In this lesson, we're going to learn a new way to describe chiral centers using what's known as Rns assignments. And this is based on the Kohn-Engold Prelog system, which is a system essentially developed to prioritize groups. And we're going to use this for chiral centers, and then later on we're also going to use it for assigning double bond configurations. So consider the two enantiomers I have drawn below, and we have our mirror plane right here. We have one enantiomer on the left and one enantiomer on the right. And you know how to do IUPAC naming for basic molecules, and without letting the three-dimensionality of this throw you off, our parent here is ethane, and on carbon 1 we have a bromo and a chloro. So if you were writing the IUPAC name for either one of these, you would write 1 bromo, 1 chloro, ethane. But that's not enough information, because we have the chiral centers. These two things are stereoisomers, and they are different molecules. For that reason, we need to be able to further define the name to tell the reader which particular enantiomer we're describing. And that's where the Rns assignments come in. In this first enantiomer, the chiral center has an S configuration, or an S assignment. In the other enantiomer, the chiral center has the R assignment. And that brings us to an important feature, that enantiomers will have opposite Rs assignments. If one molecule has an S assignment, its enantiomer will have the R assignment. And the way you tell this to the reader is you start the IUPAC name with the particular Rs assignment assigned to the chiral center. Now, what if you have multiple chiral centers that you have to deal with in a name? So here we have 2. If you are generating the IUPAC name for this, of course we'll number from left to right. The configuration of these chiral centers, we have on this first one an R configuration. On this second one, an S configuration. So when you write the name for this one, you need to tell the reader the location for each configuration. So you would start the name for this one. You put in parentheses, you would say 2R, 4S. So when there's multiple chiral centers, you include the number. And then just the rest of the IUPAC name as usual. So how exactly do we generate these RS assignments? There's a systematic approach that you want to take, and we're going to do this by working with the example here on the right. And our first step is just identify the 4 atoms that are directly attached to the chiral center. So in this molecule, here's our chiral center, and we want to identify the 4 atoms directly attached. We have a hydrogen, a chlorine, a bromine, and a carbon directly attached to the chiral center. Our next step is to prioritize these atoms, and we prioritize them by the atomic number. So we'll have to use a periodic table to help us out here, and we're going to give the number 1 priority to the highest atomic numbered atom, and then we'll go 2, 3, and 4 to the lowest atomic numbered atom. Let's bring up the periodic table here for just a minute to help us out. And the atoms we're dealing with: hydrogen, carbon, bromine, and chlorine. And remember from general chemistry that we get our atomic numbers right from the periodic table. So hydrogen has an atomic number of 1, carbon 6, chlorine 17, and bromine 35. So based on that, of these atoms, the one with the highest atomic number is bromine. So we want to give bromine our top priority, priority 1. So I'm going to put a 1 by the bromine. Next is chlorine with an atomic number of 17. That's priority 2. Then comes carbon with an atomic number of 6. And finally, our lowest priority group is hydrogen, which is priority 4. If you have a hydrogen on your chiral center, it's always going to be your lowest priority group. Okay, our third step is that we have to rotate the molecule so the priority 4 group is in the back, meaning so it's on a dash. The easiest way I find to do this is by just finding a group to hold constant and then rotating the other 3 around. So the way I'm going to get this priority 4 group to the back is I'm going to hold the CH3 group constant in place, and the other 3 groups we can move around clockwise or counterclockwise. So what I'm going to do to get the hydrogen priority 4 to the back, I'm going to rotate it to here, the bromine out to the front, and the chlorine over here into the plane. When we do this, what you want to do is draw your main tetrahedron just like you have before. So I have my 2 bonds in the plane, my dash in the wedge. My methyl group, I'm leaving it right where it was because that's the one I held constant. But then my hydrogen was rotated to the back. The bromine was rotated out. And the chlorine rotated into the plane. Now let's just retranscribe our priority numbers. Here's priority 4, 1, 2, and 3. So now we have this set up the way we need it with the priority 4 group in the back. So for our final step, to get our RNS configuration, we have to draw a curved arrow from priority 1 to 2 to 3. If our arrow goes clockwise or to the right, we assign an R configuration. If our arrow goes counterclockwise or to the left, we assign an S configuration. So for this particular example, let's start and put our pencil down on priority 1. And I'm going to draw an arrow from 1 to 2 to 3. That arrow goes around counterclockwise or to the left. So that means this chiral center has an S configuration. And that's the basic steps we're going to follow for all of these examples. All right, we're going to see a few subtle points when you have some ties and things like that, but just follow these steps carefully in order and you'll be able to assign any of your RNS configurations. Let's do another example here. We have our chiral center. Identify the atoms directly attached. We have an oxygen, hydrogen, nitrogen, and carbon. Once again, for reference, let's look at the periodic table. And based on the atomic numbers of these things, oxygen is our highest atomic numbered atom, atomic number 8. So that will be priority 1. Right. Next we have nitrogen, which is atomic number 7, priority 2. Carbon, which is atomic number 6, that's priority 3. And hydrogen, atomic number 1, that's priority 4. Now we have to get our priority 4 group to the back, and there's a couple of ways you can do this. One way you could do this, if you're comfortable, is just to flip this molecule over horizontally, and that'll flip this OH to the right side, this ethyl group to the left side, and that horizontal flip will put the hydrogen back and the NH2 out. So that's one way to do it. Another way is similar to how we did the previous example, and that's what we're going to do in this case, because it seems to be a little more foolproof and a little bit less likely for people to make mistakes when they follow this route. But let's hold one group constant and rotate the other 3. So since the ethyl group's kind of our biggest group that I don't feel like moving, I'm going to hold that one in place. Then I'll rotate the other 3 groups around cyclically, which means I'm going to rotate the hydrogen to the back, the nitrogen into the plane, and the OH out. When we do that, we still have our ethyl group here. Then we have our wedge and our dash, but after that rotation, I have the OH up here, the NH2 in the plane, and the hydrogen back, which is where we want it. Okay, just relabeling this with our atomic numbers. We've manipulated the molecule so that priority 4 group is back. Now, all you need to do is draw your curved arrow from 1 to 2 to 3. This arrow is going around to the left or counterclockwise, so that means this chiral center has an S configuration. Right, but this is a good place that I can teach you a trick you can sometimes use. Right, but this trick works if and only if the priority 4 group is pointed out. So the priority 4 group has to be on a wedge for this to work. The trick is, don't move it back, okay? Just draw your arrow from 1 to 2 to 3, and then give the opposite assignment of what it appears. So if we look at our original molecule again, we have it with this hydrogen, priority 4, pointed out. So then, let's draw our arrow from 1 to 2 to 3. And this is going around to the right. It looks like R, but this hydrogen is out, or I should say the priority 4 group is out. So it's actually the opposite of R. It's actually the S configuration. So that makes it a lot simpler. Just make sure you're careful, because if the priority 4 group happens to be in the plane, you cannot use this trick. You'll have to just do a regular rotation to figure it out. Now in some cases you might run into a situation where 2 atoms have the same atomic number. Let's look at this example down here and we'll see how that happens. Here's our chiral center, and let's go ahead and highlight the 4 atoms directly attached. We have an oxygen, a hydrogen, a carbon, and a carbon. Well, how are we supposed to prioritize these if the 2 carbons have the same atomic number? So what you want to do is compare the atoms attached to those carbons, or whatever atoms they might be. If they're still a tie, and we'll see an example of that in just a minute, move out 1 atom and do another comparison. So with this one, the 4 atoms directly attached to the chiral center are an oxygen, a hydrogen, a carbon, and we'll say carbon A, and carbon B. Now, based on atomic numbers, you can go ahead and say that the oxygen will be priority 1, the hydrogen will be priority 4. It's just the 2 carbons we can't differentiate yet. So what you want to do is look at what's attached to each of these carbons. On carbon A, if I draw everything in, I have those 2 hydrogen. So what's attached to carbon A? We have an oxygen, a hydrogen, and a hydrogen, in addition to the chiral center, but we don't really need to worry about it because it's also attached to carbon B, so it's not going to be something that will help us differentiate. So attached to carbon A, let's write what we have. We have O, H, and H. Okay, now let's look at carbon B and see what atoms are attached to it. On carbon B, we have a carbon, and a carbon. What you want to do is look at all of these atoms and see if anything wins by atomic number. Well, carbon A has an oxygen which has a higher atomic number than any of these three carbons attached to carbon B. For that reason, it gets priority. So that'll be number 2. Carbon B will be number 3. We now have our atoms prioritized. If you need to move priority 4 to the back, you would do that, but in this case it's already to the back, so we don't have to worry about that. Now all we have to do is draw our arrow, and we have a curved arrow going from 1 to 2 to 3. That's going around to the left, so this one has an S configuration. Okay, here's another example where we have our chiral center. Right. First thing, identify the 4 atoms directly attached. Bromine, hydrogen, carbon, and carbon. Right, so, kind of like the last example, it's pretty easy to say bromine's priority 1, hydrogen's priority 4, but the 2 carbons, you can't differentiate them. So what we're going to do is, just like before, look at what's attached. Well, this carbon here, it's attached to the chiral center, which we're not going to count, but it's also attached to a carbon, a hydrogen, and a hydrogen. So let's write those down. Okay, now let's compare that to this carbon. It's attached to a carbon, a hydrogen, and a hydrogen. Well, guess what? We have a tie. So if you run into a tie, just move one step down the chain and do another comparison. So now what I'm going to do is move to this carbon and this carbon to compare. So let's see what is attached to each of these. Right? Well, we have the attachment that leads back to the chiral center that we're not going to count, but this carbon's attached to a carbon, a hydrogen, a hydrogen. Okay, on the other side, we have the attachment back to the chiral center that we're not going to count, but then this is attached to a carbon, a hydrogen, and a hydrogen. Well, we have another tie. If that's the case, move one step further down the chain and compare. So we'll move to here and here. And let's once again write what's attached. On this one you have a carbon, a hydrogen, and a hydrogen. on this one on the right, we have a carbon, and a hydrogen. We finally have a tiebreaker. And on the left side there's one carbon, on the right side there's two carbons. Two carbons beat one. Even though they have the same atomic number, two are better than one. So for that reason, this right side gets the priority 2 designation, and the left side priority 3. So this example shows where you have to be careful, because if you weren't careful, you may have just looked at this and said, oh, well, I have an OH over here, so that must be a higher priority. But in fact, using our rules very carefully and very systematically, it was this right side that got priority over this side with the OH. And that's because we reached the tiebreaker before we ever got to the OH to even consider it. So just look very blindly and carefully down your chain stepwise. Alright, so this one you're pretty much set up because the hydrogen is back and that's where you want it. So now all we need to do is draw our curved arrow, and we go from 1 to 2 to 3. That one is going around to the right. So this is our configuration. One final example that's going to show us how to treat double or triple bonds. And what you want to do is, in terms of priorities and attachments, consider double bonds as 2 separate single bonds to that atom, or triple bonds as 3. So just for example, if you just have this carbon-carbon double bond, the way you can essentially view that is instead of a double bond, just 2 separate single bonds to carbon. So essentially, there's one bond to the carbon, there's a second bond to the carbon. So we're viewing it as one bond to the carbon, a second bond to the carbon. Alright, so let's look at this example down here. We have our chiral center. Again, as we've been doing, look at the atoms directly attached. We have a bromine, hydrogen, carbon, and carbon. So it's easy to say priority 1's bromine, priority 4's the hydrogen, but how about the 2 carbons? What you want to do is think about what's attached. This carbon at the top, if it helps, you can draw in the hydrogens. Right? This carbon is attached to an oxygen, a hydrogen, and a hydrogen. Okay, now let's look at this one. It's attached to an oxygen, and we'll say an oxygen and an oxygen, since this double bond counts twice. It counts as 2 single bonds to an oxygen. So effectively, that carbon's bonded to 3 oxygens. The 3 oxygens wins. So priority-wise, that'll be priority 2. This one will be priority 3. Now, you can use your trick here because the hydrogen is out. But I do want to show you kind of one other way to simplify a complex molecule if you do have to manipulate it to get the priority 4 group to the back. A lot of times what I like to do is just simplify it as just a basic tetrahedron. Here's my tetrahedron, and then on that tetrahedron just write your priority numbers. We have 1 back, 4 out, and then 2 and 3 in the plane. And then this small molecule here is really easy to work with and manipulate. So what I can do, let's say we hold 3 constant, then I can rotate 4 to the back, 1 into the plane, and 2 out. Once we do that, we still have 3 we held constant, 1 over here, 2 here, and 4 here. Now just draw your curved arrows. This goes around to the right, which tells us an R configuration, and that's the configuration of the original molecule. Now again, this one probably would have been easier just to use the trick. So hydrogen or priority 4 is out, so we would go from 1 to 2 to 3. It looks like S, but since priority 4 is out, it's actually R. One kind of special case to know is if in a molecule you have a double bond and this isopropyl group that essentially, based on what we talked about, would tie, because here's a carbon attached to 2 carbons, and if we treat the double bond as 2 separate single bonds, this carbon's attached to 2 carbons. So how do we know what to do here? Basically, if you run into this, specific circumstance, the double bond wins in terms of priority. So for example, if you were to have this molecule, the oxygen's priority 1, the hydrogen's priority 4, and then these 2 groups, based on all the rules we've discussed, end up tying with one another, we give the double bond priority. So that's 2, and that's 3. So then draw your arrow. This one goes around to the left, so that's an S configuration.